on.
Today we'll be talking about the periodic table. As you remember, Dmitry Mendeleev came up with the format where we had families and rows, and his periodic table did not include the noble gases. And there were spaces in his periodic table as well, where he predicted where an element should be, and yet it had not been discovered. So in this periodic table that we see before us today, we have a complete periodic table, and we'll start with an orientation and look at things you should know and remember about this periodic table that'll be helpful to us when we start considering how compounds form and also how to balance chemical equations. So let's start out with the simplest element, hydrogen. And if we look at the box here, we see the number 1, and this number 1 represents 1 proton. That means in the nucleus of hydrogen, there is 1 proton, and that proton defines what we call the atomic number. Underneath this, we see the symbol, the capital H, and in our periodic table of elements, all elements begin with a capital letter. Some have more than 1 letter. The second letter is never capitalized, it's always lowercase. Below, we find this spelling of the element, and then below that, we have the average atomic mass. Now, we notice here that the average atomic mass is very close to 1. Now, what does that mean? It means that hydrogen has several isotopes. To understand that, we need a definition. Isotopes refer to the same number of protons, but a different number of neutrons. Protons and neutrons each have a mass of 1 atomic mass unit. So looking at this, hydrogen we see is 1.008. Hydrogen has 3 isotopes, protium, deuterium, and tritium. Protium has no proton, 1 proton and no neutrons. It has a mass of 1. Deuterium has 1 proton and 1 neutron. It has a mass of 2. Tritium has 1 proton and 2 neutrons for a mass of 3. As we look at this number here, 1.008, we see that the most common form of hydrogen has only 1 proton. So it has a mass of 1. That's the most common kind of hydrogen, the most common isotope of hydrogen. Now, as we continue across the table, and this orientation across the table we call a row or a period, we find helium. And helium, as we see, has the atomic number of 2. And if you look over here to my left in the larger blue block, you can see more clearly as I indicate with my hand here that helium has atomic number of 2, meaning it has 2 protons. Its symbol is He, and there's your spelling. And then you see the average atomic mass is 4.0026. Helium then would usually have 2 protons and 2 neutrons, each proton and each neutron having a mass of 1 for a total mass of 4. Our next element in the next row is lithium. I've highlighted lithium here. You can see it has an atomic number of 3, and it's interesting. To the right, you see the numbers 2 and 1. Now, what does that refer to? That refers to the electron configuration of lithium. Since lithium has 3 protons, it attracts 3 electrons. And the orientation of those electrons would be 2 electrons in the first shell and 1 electron in the second shell. Lithium has an average atomic mass of 6.94, which we recognize is very close to the number 7. So as we look at lithium and consider that it has 3 protons, the most common isotope of lithium must have 4 neutrons. 4 plus 3 makes 7. So 6.94 is almost 7. 3 protons plus 4 neutrons would give us a mass of approximately 7. Now let's look at where lithium sits underneath hydrogen. This is significant. If we go back to look at hydrogen and look at the electron configuration, we see that hydrogen has only 1 electron in its valence shell, and lithium also has 1 electron in its valence shell. If we continue downwardly, we find sodium. Sodium has an atomic number of 11, 2 electrons in its first shell, 8 electrons in its second, and 1 in its third. A total of 11 electrons, each electron being attracted by the positive charge of the protons located in the nucleus of sodium. 2, 8 plus 1. Just like lithium, sodium has that 1 extra electron in its outer shell. And we can see the pattern. If we continue down, we see potassium, atomic number 19, 19 protons. 2, 8, 8, 1 attracts 19 negatively charged electrons. Again, the first shell fills with 2, the second with 8, the third with 8, and finally we have the last shell with only 1 electron. And just like sodium and lithium and hydrogen, it will be an element that wishes to let that electron go. It doesn't feel comfortable or stable with that electron in its outer shell. So as we see, this entire group or family or column shares a chemical characteristic. Each of them have 1 electron in the outer shell, and they will very quickly lose this electron if they can. They'll give it away to some other element that would like to have an electron. Now, when that happens, each of these, francium, cesium, rubidium, potassium, sodium, and lithium, and hydrogen, will become what we call ions. They'll become a positively charged ion, and we have a term for a positively charged ion. We call that a cation. Now back to lithium. If we start going across the table, remember across the table is called a period. It's also called a row. As we go across the period, we have beryllium, which is atomic number 4, and keep going to boron, carbon, nitrogen, oxygen, fluorine, and finally neon. What you should know as we go across the table and we look at these numbers, 3, 4, 5, 6, 7, 8, 9, and 10. What we see in those numbers is an increased number of protons. As we go across the table, every element has 1 more proton than the element before it. So we have a couple other interesting families here. Carbon, we often call family number 14, we often call the carbon family. Why? Because carbon sits at the top of this group of elements. Family 15, we sometimes call that the nitrogen family. Why? Because nitrogen sits at the top of this group of elements, and they all have the same characteristic. They all have the same number of electrons in the outer shell. Then we have the oxygen family, family number 16, and this very interesting family number 17. We call this family the halogens. You probably have heard of halogens commonly in headlights, halogen headlights, very bright. And maybe you've heard of chlorine. You go swimming and you want to have a pool that's clean, so it's chlorinated, or maybe it's brominated. Or perhaps you've been to the hospital with an injury and had to have a surgery or some sort of incision, and they made the wound clean by using iodine. And see, all of these are in a row. And the final one is astatine. Now, one thing you should notice as we go from top to bottom, looking at this column, fluorine has an atomic mass of only 18.9. Then chlorine, 35.45. Bromine, 79.9. Iodine, 126. You can see the pattern. As we go down, the masses increase. So these are much larger, heavier atoms, but they all have one thing in common, just as the first family had something in common. These elements have configurations where their outer shell is almost full. Looking in the green box over here to the left, we see the capital F with the 9, and the configuration to the right, 2, 7. Configuration 2, 7. Now that means there's 2 electrons in the first shell and 7 in the second shell. Well, fluorine is very unstable because fluorine with its 7 electrons in its outer shell is seeking to find that extra electron. Now, where can it find an extra electron? Perhaps it could take an electron from lithium or sodium or potassium or even hydrogen. And if it did so, then it would feel as though it had the configuration of its next door neighbor, which is a noble gas, neon. If fluorine were to take on an extra electron, that would mean that it would have 9 protons and 10 electrons. So overall, if you consider plus 9, negative 10, you can see that fluorine would make a negatively charged ion. Chlorine makes a negatively charged ion. Bromine makes a negatively charged ion. Iodine, all for the same reason. All of these halogens, when they pick up that one extra electron to fill their outer shell, become more stable. They become like noble gases. And really, that's kind of a pattern that we see here on the periodic table that drives eventually the formation of compounds. We consider that each one of these elements wishes to have a complete outer shell to be like a noble gas. When we reach the final group here, 18, you recognize these characters: helium, neon, argon, krypton, xenon, and radon. These are very stable. They have a special status. We call them inert. That means that they really don't interact with the other elements very much at all because they don't need to. They have no need to because their outer shells are filled with electrons. And you probably have heard of neon signs. I don't know if you've heard of argon and torches with welding. And when you hear of krypton, you usually think of Superman, but it's not kryptonite, it's just krypton. Sometimes we use xenon around situations where we don't want chemical reactions to take place as some sort of a buffer to surround chemicals so that they don't interact. Purposely, we do this. Radon is kind of an unfortunate gas in the sense that it can cause cancer. You can't smell it, you can't taste it, you can't see it, and yet some of our homes in northwestern Ohio have radon gas, which comes up from the rock underneath our homes. So you have to have that tested, and many people do have their homes tested for radon gas. Well, let's go back again to the other side. See, once we go across and hit to neon, once we hit neon, that outer shell is full. We can't go any further to the right. So we have to go to the next row or period and start over again. So we go to sodium. And here we see sodium again with only 1 electron in its outer shell. Magnesium then with 2, and aluminum with 3, and silicon with 4, and phosphorus with 5, sulfur with 6, chlorine with 7, and then we come to argon again with a full outer shell. This pattern continues. In fact, we have a special word that we use to describe this pattern. It's called an octet. Some of you play the piano or play an instrument. You've heard this word octave. If you didn't play a piano or play an instrument, you probably have heard the word octagon. That's an 8-sided figure. So this figure 8 refers to something that happens quite frequently in nature. Here in the periodic table, the octet rule refers to filling the outer shell when you have 8 electrons. So passing on beyond argon, we go to the row 4, period 4, which begins with potassium and goes clear over to krypton. And we continue this pattern, and then we want to look at this right here. We see in this model that the orange group has a name. So you want to write this in your notes. This orange group is called the alkali metals. That's spelled A-L-K-A-L-I metals. A-L-K-A-L-I metals. Perhaps you have heard this word alkali. Sounds like a battery maybe? Alkaline batteries. Well, alkaline batteries contain these metals. Then right next door to the alkali metals are the alkaline earth metals. They're very similar in that they will also become cations. Instead of having one electron in its outer shell, they have 2 electrons in the outer shell and are very willing to give away those 2 electrons to become cations. Now, the way this table is designed, we want to keep it on one page. So if you look at 57 through 71 and 89 through 83, we have what are called the lanthanoids and the actinoids. These are heavy metals, and if we did not move them down lower on the periodic table, as you see them here listed, why, it would make the periodic table very, very wide, and it wouldn't be practical. So for publishing purposes, we take those elements and we move them down. You can see the numbers 57 through 71, and then 89 through 103 for the actinoids. Now in the middle of the table, we have what's called the transition metals. This, of course, means they're transitional. They're somewhere between the right side and somewhere between the left side. Right, kind of in the middle, they're in transition. And these, some of these you'd recognize: cobalt and tungsten, which we have in our light bulbs; platinum, a very valuable metal, as is gold and silver; and Hg. Now, something special about Hg, when you look at this table, you'll notice that Hg is given in the color blue. And that means, in this table, that mercury at room temperature is not a solid, is not a gas, but is a liquid. There's only a couple liquid elements at room temperature, and you can find them both. Bromine, a halogen over number 35, that's liquid at room temperature, and mercury is liquid at room temperature, number 80. All right, let me go to the next group. It's called the post-transition metals. They sit right next to a real interesting group called the metalloids. Now, if you look at that green color there, it looks like a step ladder, doesn't it? And that's an easy way to remember it. Boron, silicon, under silicon, germanium, next to germanium, arsenic, underneath arsenic, antimony, next to antimony, tellurium, and then our final step, astatine. All of those elements are sort of like nonmetals, and they're sort of like metals. How are they sort of like metals? Well, some of them can be shiny, and some of them are dull. Some of them, or actually all of them, can conduct electricity, but not as well as the other metals do. One thing about all of these, unlike metals, they're not malleable. If you take a hammer and hit one of these elements, it'd be like chalk. It would break into little tiny particles. We call that brittle. So this stair-step pattern, these metalloids are brittle. They can conduct electricity. They are shiny and or dull. And they're very useful, particularly for some of the software and the computers and things that you use today. In your phones, we have a frequent use of silicon. And you've probably heard of Silicon Valley, where a lot of silicon has been used to take us into the computer revolution that you're all part of. Now we keep going to the right, and we have nonmetals. So it's important later on when we start naming elements that we know which are the metals and which are the nonmetals. Nonmetals combine, when they combine, they make what's called covalent molecules. That is, that the electrons, rather than being given, as we saw with lithium and sodium and potassium and fluorine taking and chlorine taking, rather than giving and taking, this group shares. So when we make a covalent bond, it's between a nonmetal and a nonmetal. So that's a very special group. You notice that most of them are gases. But interestingly, carbon is in that group, and it is not a gas. And bromine is in that group, and it is not a gas. It's liquid at room temperature. And of course, iodine, you've seen that too. So these are the nonmetals. And then, as we had said earlier, Mendeleev did not have this final group in his table at all, because these were discovered after the time that he'd completed his original table. This last group is the noble gases. And clear over to the right, and as we had mentioned before, they don't interact. So, what is the value of this periodic table for us? Everything on Earth is made up of these elements. In fact, if you were to consider yourself, you are mostly water, hydrogen, and oxygen, and you're a carbon-based creature. So all of your major molecules, we call them macromolecules, your proteins, your carbohydrates, your amino acids, your proteins, and also your nucleic acids, are all carbon-based. And being carbon-based, they're all going to be what we call covalent molecules. So a lot of what you see here on the periodic table, you have in your own body. You have hydrogen, and we know that lithium is often used for people who have specific illnesses because it helps the brain to stabilize, and they take medications containing lithium. You're probably aware of nitrogen being part of something we put on the fields to help grow our plants, and ammonia. And then you may not know this, but proteins all contain nitrogen, and every one of your nucleic acids include in your every cell of your body includes nitrogen. Oxygen you know about because we need it to breathe, and obviously because you're mostly water, there's quite a bit of oxygen that's stuck in you right now. You may have thought about fluorine some when you brush your teeth, because fluorine is often found in toothpaste. And we mentioned neon lights before. Sodium is an element that's found in your bloodstream, and magnesium is found in your bones. Phosphorus is in every cell of your body as part of a polyatomic ion we call phosphate. Every DNA molecule contains phosphate. So when your cells are replicating and making new cells, there has to be a supply of phosphorus there. Sulfur is also, wherever there's a protein, there'll be sulfur. So if you think about your cells, your cell membranes have proteins in them. And in order to have those proteins, the sulfur has to be there. So sulfur is very common in your body as well. Potassium is something you need for in your blood, and calcium in your bones. Potassium, I should go back and say, that helps with your nerves. Nervous signals that travel along your nerves require potassium, and your heart needs that potassium particularly to keep pumping. Iron is in your blood, carried by hemoglobin to every cell of your body. I think there's quite a few more that incidental ones, like zinc. You probably hear about zinc. You probably put that on your nose to keep the sun from burning you. Or you may take zinc tablets because you need zinc to help stay off colds, that sort of thing. Some of the heavier elements we use in medical treatments, like barium, and let's see. Well, that's enough right now. I want you to familiarize yourself with these important elements. I'll be giving you a list of the names of the elements which you must memorize because they're important to you and your body. And you'll be hearing about them in biology, and you'll be seeing them frequently as you begin to make compounds and balance equations. So this will be a task. We'll be making cards where each card on one side will have the name of the element and its symbol. The other side will have the symbol, I should say. So you have the name of the element on one side and the symbol on the other. And we will play games together to memorize both. So I hope you've enjoyed this brief orientation to the periodic table. We do want to thank Mendeleev and some of those other stars that you met in the film series, The Mystery of Matter. And they've given all this to us so that you can easily have it at your fingertips now. I want to remind you what a long process it was to pull this together and how many men and women worked and spent their lives so that you could so easily take advantage of understanding what you have in front of you. It will take you time to memorize this table, and you'll always have it at your fingertips, but it's easier for you in the long run to memorize these symbols. Thank you for enjoying this periodic table with me, and that's the end of our lecture today. I did bad. Oh well, it's gotta stand.